For this lesson, we're going to look at determining molar mass, looking at percent composition by mass, relating that to empirical formula, relating that to the overall molecular formula. So this can be difficult for a lot of students just because it's math heavy, but really the main thing is we follow a systematic approach and it's relatively straightforward. So the first question asks, how many moles are in 99 grams of iron phosphate? This formula here is what I like to use, which is number of moles is mass over molar mass. So in the question, we're given the mass, but we do first have to work out the molar mass of this iron phosphate. So the key thing to remember here is that the subscripts refer to the elements on the left. So in here, that 4 refers to the number of O's. We have a parenthetic term, and so these parentheses means that the whole lot gets multiplied by this 2. So we'd have 3 ions, we would have 2 phosphoruses, and then 8 oxygens. So when I work out the molar mass of the iron phosphate, I've got to keep this in mind. Ordinarily, you rely on your periodic table, but for this question, I supplied these molar masses, so I just use M for molar mass, but different textbooks, different instructors will use different lettering for that. But these are the molar masses here. So my first step is going to be work out the molar mass of this compound. So I won't worry about writing it all out, but I'll just write the molar mass. And so it's going to be 3 times my iron molar mass, which is 55.85. I'm going to add to that my 2 phosphoruses. I'm going to add to that my 8 oxygens. So I'll put this all on one line so it's a bit easier to see. Okay, and so according to my calculator, I have 357.49. And then the units for this are grams per mole. Sometimes you'll see it expressed as AMU, and that's okay. But it's 357.49 grams per mole. And so the mole, we can talk a little bit about that now, is a quantity that is used for convenience in the same way that a dozen is 12 eggs or rolls or whatever it was referring to, and a score is 20 and things like that. The Avogadro's number, which is this number here, the Na number, is just a quantity that makes the masses of the elements come out to a nice number. So it was originally defined as the number of atoms in 12 grams of carbon-12. So we continue to use that, and it makes the numbers on the periodic table reasonably easy to understand. So when we look at hydrogen and it's got a molar mass of 1.008 grams, that means that 1.008 grams of hydrogen has this number of atoms in there. If we looked at this case with iron here, that's saying that 55.85 grams of iron has 6.022 by 10 to the 23 iron atoms in it. So those numbers that come out in the periodic table, they're easy masses to work with, and so this is the system we use. So back to the problem. So if we want to work out the number of moles that's in the 99 grams of this iron phosphate, I'm going to use this formula here, and we would get at 99 grams, and then and divide that by our 357.49 grams per mole. I'll just put a line in there for the separation of these two. Okay, so this will be the division here. And then, according to the calculator, we would have 0.2769. Okay. Now the units. Just a word on units. Notice how I've got grams in the numerator, grams per mole in the denominator. Because you've got a division in the division, if that makes sense. Depending on how familiar you are with your fractional rules and things like that, this grams of a mole in the denominator would come out to the side and then be inverted and multiplied, if that makes sense. If that doesn't make sense at all, then don't worry about that too much. But that's why the overall units, the grams are going to cross off, but it's like you've got a per mole, and that per mole becomes a mole. Again, if that doesn't sound too straightforward, just don't worry about that part too much. But if it does, that's why the actual units overall are going to be your mole. Okay, that's the first part of the problem. The next part of the problem is asking how many molecules. And so the number of molecules is going to be the number of moles multiplied by that Avogadro's number. So the number of molecules is just going to be, and by the way, I should finish this first problem off first because it's not quite correct at the moment. We don't have the correct number of significant figures. If you remember from the original question, we had 2 significant figures. So really this should be okay, so 0.28 mole. When I do my number of molecules and all the way through these problems, I don't round off till the end. So even though you might be reporting to a specific number of significant figures, you carry through as precise a value as you can all the way through. So here when I'm working out my number of molecules, I'll actually use what's on my calculator. So on my calculator, I have quite a large number of decimal places there. I will use that and keep that number on the calculator when I do this next part of the calculation. So try and minimize any round off error as I go. So I'll write down here that I've got 0.2769 multiplied by this Avogadro's number. Okay. And I should probably have the units in there. So the units here are mole, and the units here are going to be your grams per mole, so your per mole. And so in science, we often like to use, I'll have to fix this up here, negative exponent when we're dealing with powers that are being divided. So if that's not too familiar with you, the -1 means that it's really 1 over a mole here. And so what's going to happen is these are going to cancel. The mole and the per mole are going to cancel. Okay. And I might write this on the line here so it's a bit easy to see. So overall, and like I said, I'm using the value that's on my calculator. I've still got it there. And I multiply that by my 6.022. And then times 10 to the power of 23. And I get 1.6676 by 10 to the 23. But I'll just report this to two significant figures because, again, the original in the question had two significant figures. So I'll just put 1.7 by 10 to the 23. Okay. I can put molecules here. Okay, so the Avogadro's number is just simply multiplied by the moles, and you'll get that. For the next question, it's what is the percentage of O in CO2? And we can work it out for carbon as well here, but the question at the moment is asking for what the percentage of just O specifically is. So here, we look at the overall molar mass of the carbon dioxide. So from memory, that's going to be about 44. So we have an overall molar mass of the carbon dioxide. And then out of that molar mass, we would look at the molar mass of O in there relative to that total molar mass. So carbon's 12.011 as for a molar mass. So the molar mass, and I'll just put this in here, the CO2 is going to equal our 12.011 grams per mole for the carbon plus, now we've got two lots of the oxygen, which is 16.00 grams per mole. And so we look at that total, and we're going to have $44.01 grams per mole. Okay. Like I said, that would be the total mass of 1 mole. So 44.01 grams would constitute 1 mole of carbon dioxide. And so in that, you could look at the oxygen relative to it. And because there's 32 grams of oxygen in there, and the percent mass is just going to be that. Oops. So I forgot to press shift there. So percent mass is just going to be the 32. I won't worry about the units now, but the 32 divided by the 44.01, and we get about 73%. And there weren't any significant figures specified in this problem. So generally, we just go to what we use in the data, which is about 4 significant figures. So it would actually be 72.71. Percent oxygen. Okay, I'll put it on one line if you like. Okay. So hopefully that is easy enough to follow. And if we did work it out for carbon, we'd find that the balance for the carbon would just be the 12 divided by the 44 roughly, and then you would get the right answer for the carbon percentage as well. Which would give you 27.3% roughly, just quickly on the calculator. Okay, so on to the next problem. we have a substance which is 54.5% carbon, 36.3% oxygen, and 9.15% hydrogen. What's the empirical formula? So the easiest way to do this is just to assume we have 100 grams of substance. It doesn't really matter how much you assume, but the calculation is going to be easier if you use 100 grams. Because if you add 100 grams, then you must have 54.5 grams of carbon, if that makes sense. Just because you got that percentage times by 100 grams, then that's going to give you the grams of carbon. So my first approach for this, because I'm dealing with empirical formula, and so formula, we're sort of going back to mole ratios now. Rather than looking at masses, we're looking at the mole ratio. So in a way, in the previous question, we had the mole ratios with CO2. It was saying in the formula of CO2, you got one mole of carbon compared to 2 moles of oxygen, at least in a ratio setting. And so here we're going to look at a mass going back to a molar ratio in order to understand what the empirical formula is going to be. So again, I'm just going to assume 100 grams. So maybe I'll write that in there so that it's explicit. Okay, so we'll go assume 100 grams mass. Okay, so now that would mean that I won't worry about writing out the mass of all these. You'll just know that it's pretty much going to be what the percentage is just going to become the grams. So when I'm now going to look at the number of moles of carbon, so put in my number of moles of carbon in the subscript C, and that's going to equal this 54.5 grams divided by the total molar mass. And you can see in the question, the total molar mass is, well, the total molar mass is 88.11. We don't need that part yet. We're just working out the empirical formula. So we're going to not divide by the total molar mass, but we're going to divide by the molar mass of carbon itself. Okay. So this is going to be for our number of moles of carbon. And that gives us 4.54 mole. Again, these units, because we had the grams over the mole, and it's really division overall, and I should probably put these in parentheses to avoid any confusion with that. You're going to actually have mole as your unit. So that's our number of moles of carbon. We can do the same thing with the number of moles of oxygen. And so here would have a 36.3. We know it's 16.00 grams per mole. And then that's going to give us 2.27. Mole. The last one, where we can work out our empirical formula, would be the number of moles of hydrogen. And so that equals 9.15 grams divided by our 1.008, or 1.01, how you want to look at it, grams per mole. Which is about 9.08 mole. Okay. So let's just recap what we've done so far. So we've got our percentages, and those percentages are based on mass. We assume 100 grams, but you could assume any amount, but the calculation is going to be easier if you just assume 100 grams. So now you've got your masses, pretty much just the same as the percentages, but now they come out to grams. You divide by the molar mass of each individual element, giving us now the number of moles of each element. And and so now really what we'd have is an empirical, well, we're nearly at the empirical formula. What we've really got so far is something like this. Okay. Again, this is looking at the ratios here. So we've got carbon 5.54, oxygen 2.27, hydrogen 9.08. So we're looking at the mole ratios here. And obviously that's not too easy to work with. So it doesn't look very good. And so what we want is really to make these all whole numbers. And so the way you do it is you divide through by the smallest number. In this case, the smallest number is 2.27. So I divide each of these numbers by 2.27. Obviously, with the oxygen, the 2.27 is just going to give you a 1. That's why we start there. And so if I divide through by those numbers, and I would encourage you to do this yourself, we'd have the 5.54 divided by 2.27, and that comes out to 2, actually. So it would be carbon 2. Oxygen, like I said, is clearly just going to be a 1, so I won't worry about putting a subscript there. And then we have our hydrogen. Let's look at that. 9.08 divided by 2.27 equals 4. So this right here is our empirical formula because there's nice whole numbers. Let's say you did this procedure with a different problem, and when you did that procedure, dividing through by the lowest number, you actually ended up with, say, 2.5 and an O and, say, a 4.5 or something. You still aren't at whole numbers yet. Then you would just multiply by a number, and sometimes it takes a bit of trial and error, but you would multiply by a number that ends up giving you a whole number. So again, if this happened to be 2.5, I'd just double it probably. And so I'd double everything through there. So then you'd have carbon 5, and you'd have oxygen 2, and I think I said the hydrogen with 4.5, that'd become hydrogen 9. That makes sense. In this problem, we've arrived at the empirical formula as it is, but if in some other problem you ended up with non-integer numbers, so it might end up with a half or even a third or something, as well as your number there, then you would know to multiply by 2 or 3 or whatever you need to do to get to those whole numbers so that you can report your empirical formula. So I'll just write empirical formula here. So that we know that's what we've got. But the empirical formula is the lowest mole ratio within that formula, but not necessarily the actual formula. Okay. So to get the actual formula, we're going to look at the molar mass. So in the question, we're given that the molar mass is 88.11. So what it means is there's in the actual molecule. Now, the actual molecule is going to be some multiplication of that empirical formula, okay? So the empirical formula is the smallest building block that gives you the mole ratios. And so in the actual molecular formula, you're still going to have the same mole ratios. It's still going to be a ratio of 2 carbons for every oxygen for every 4 hydrogens. okay? That won't change. It's just that the actual molecular formula would show you how many of these carbons, oxygens, and hydrogens constitutes one molecule, if that makes sense. So the way to do that is to work out the molar mass of this empirical formula. And so the molar mass of the empirical formula is going to be our 2 carbons. I guess I'll put it here. So don't run out of room. So to save room, I'll just avoid the units for the time being. Okay. So this is what the molar mass of the empirical formula is. And I get 44.05 grams per mole. So that's the molar mass of this empirical formula. And so we compare that to the actual molar mass of the actual formula, of the actual molecule, not the empirical formula, but the actual molecule. And you just do a little side calculation. So just comparing those two. Looking at that, we can see that, I mean, I didn't really need a calculator for that one. You can see that it's going to come out to be equal to 2. So what does that mean? That means that in the molecule itself, there are 2 empirical formula units, if that makes sense. So the overall formula for the molecule must be the empirical formula multiplied by 2. So overall, what we've got is C4 O2 and then H. So C4O2H8 is going to be our overall formula. Okay, so once again, these are the 2 things we're looking at here to answer the problem: the molecular formula and the empirical formula. Okay, so a lot of students struggle a little bit with the math because it is a little bit math intensive, but the main thing to do is to be systematic in your approach. So as you go through, just follow those procedures, and practice is what's going to help become very proficient with this.